Okay, here we are, onward and upward. We just finished our discussion of how to numerically summarize the concept of average, or well, let's just say average or center, in terms of a quantitative variable. Now we're going to move on to a discussion of how we might measure the spread or the variation in a particular quantitative variable. But before we get around to doing that, let's kind of look at a couple examples that one motivate the need for us to actually measure such a thing. So two different sections of Math 121, both of them absurdly small. Each section only has 3 students. The first section, the 3 students take their test. They get a score of 70, 72, and 68. So the question is, what's the mean and what's the median? Now, don't fall for the trap and say the median is 72. Remember, we have to order the numbers. If we order the numbers, they go 68, 70, 72. The middlemost number, once they're ordered, is 70. So the median is 70. I leave it to you to verify that the mean would be 68 plus 70 plus 72 divided by 3. If we do that, we get 70 also. So for this section, the mean and the median are the same. They're both 70. Now for section 2, we have the same result, essentially. If we order our numbers, we'll see that the median is 70. And the mean is 70 plus 100 plus 40, that's 210. 210 divided by 3 is, it's 70. So the mean and the median are 70. What's the implication of this? The implication of this is going to be on the following slide. But it's essentially this, right? If we only look at measurements of average, it looks as if these 2 sections have performed identically. It looks as if the 2 sections are identical. But we know that that's not true. There's a fundamental difference between those 2 sections, and it's a difference that's probably apparent to us immediately. What is that difference? Exactly. The 2 sections differ with respect to their variability. In the first section, we would say that the 3 students essentially scored about the same, right? 68, 70, 72, that's all round about the same scores. Whereas in the second section, we would say there is a lot of variability. There's a lot of spread. There's a lot of dispersion, right? There's one student who completely bombed the test, got an F. There's another student who completely aced it, right? And then we have Goldilocks somewhere right in the middle. So, just to reiterate, if we report only the mean or the average of the tests, it looks like they performed not just similarly, identically, but again, we know that's not the case. So this motivates something. What does it motivate? It motivates the need for something more. We need to be able to describe another property, another characteristic of a quantitative variable. And that property or that characteristic that we want to be able to measure or describe is its randomness, its variation, its dispersion or spread outedness. So we already answered this question. How do those 2 sections differ with respect to their variability? We said there is very little variability in section 1. There's a lot of variability in section 2.
Okay, so now that we've motivated this quality, this characteristic that a variable can possess, this concept or idea of dispersion, of randomness, of spread outedness. The question now becomes, like, how do we go about numerically measuring this quantity? There's a few common ways of doing it. There's 2 that our book really focuses on. That's what we're going to discuss in the PowerPoint. The first is this idea of range. Very simple, very intuitive. We'll talk about that starting in the next slide. The second one, which we'll talk a little later on in this PowerPoint or video, is the variance / standard deviation. So technically 2 different numbers, I guess technically 2 different quantities, but as we'll see, they're intimately connected to one another, and as such, we're going to sort of talk about them as a collective or cohesive unit.
The range is perhaps the simplest way of calculating dispersion or spread outedness. And the range is defined quite simply as the difference between the largest and smallest value in a data distribution, right, or a set of numbers. Remember, subtraction is essentially a distance operator. So when we do the largest minus the smallest, we're saying what is the distance between the largest number and the smallest number, right? What is that range between those numbers? Because that's essentially, right, all the values are contained, all the numbers are contained within an interval of that particular size. So for example, if the test scores of section 3 of Math 121 are 60, 70, 80, 90, 100, then the range would be the largest, which is 100, minus the smallest, which is 60. So that would give us 40. Think back to section 1. Section 1 had the 68, the 70, and the 72. The range in section 1 would be 72 minus 68. The range would be 4. That's a small number indicating a small amount of variability. Section 2, I think, was what? 40, 70, and 100. So the range for there would be 100 minus 40. So the range there would be 60. There was a lot of variability, hence the range was a relatively large number. Next up is the variance. The variance is considerably more complicated to calculate than the range. Conceptually, the variance can be thought of as the average squared distance all observations are from the mean. It can be computed with the following formula. So the sample variance is often abbreviated S squared, right? So just like the sample mean was abbreviated x bar, we have an abbreviation for the sample variance, it's S squared. And it's essentially, right, there's that add 'em all up symbol. So it's saying take x, which is the observation, subtract from it the sample mean, that's x bar. Remember, subtraction is a distance operator. So that x minus x bar is saying, for every observation, find the distance that observation is from the mean. Square that distance, and add up all those squared distances. Now the one thing that's maybe a little bit unintuitive, so I have all these squared distances, I add them all up. If I want the average squared distance, it would make sense to divide by n, wouldn't it? And instead we divide by n minus 1, which is a little bit unexpected. But a couple observations. The difference between n and n minus 1 is particularly for large sample sizes, not that big a deal, right? Dividing something by 100 or by 99, right, by two numbers that differ only by 1, doesn't change the number that much, although it does change it a little bit. Mathematically speaking, it turns out, and we'll talk more about these ideas of estimation and inference later in the class, but it turns out that the sample variance is supposed to be estimating something called the population variance. And for it to do that properly, we can prove mathematically that what we need to do is divide by n minus 1 rather than the usual sort of expected n. So it's somewhat technical, somewhat mathematical, but we need to divide it by n minus 1 instead of n. But we're still sort of conceptually looking at this average squared distance. Now, you might say, average squared distance, what the cutta? Who cares about squared distances? And I would tend to agree with you. And that sort of complaint is what's going to motivate the next measurement of variation, or rather the next slide. So here's the standard deviation. The standard deviation can be thought of as the average distance, not squared distance, the average actual distance all observations are from the mean. This is often more useful than the average squared distance, which is essentially saying that the standard deviation is often more useful than the variance. Because of that, it's the standard deviation rather than the variance that's often used in practice. It's used with the following formula. Standard deviation equals S. So that's a sensible abbreviation, right? S for standard deviation. And its formula is what? It's the square root, and what's inside that square root? That's exactly the variance formula. So the standard deviation is essentially the square root of the variance. So sometimes people ask, they say, well, if the standard deviation is so useful, why do we even bother learning what the variance is? Well, we can see the variance is a stepping stone to the standard deviation. We cannot compute the standard deviation without first computing the variance. Once we have the variance, we take its square root, and that gives us the standard deviation. Right? Which indicates why we have the abbreviation S squared for the variance, because the variance is literally the standard deviation squared. That is, if I told you the standard deviation was 3, the variance would be 3 squared, which is 9. If I told you the variance was 25, the standard deviation, as we see with this formula, is the square root of the variance. So it's the square root of 25, which is 5. So we can go back and forth from standard deviation to variance fairly easily. That's something I expect you to be comfortable with. It's something I expect you to do. I often will make a test question asking you to go from one to the other. Right? If you want to go from standard deviation to variance, you just square the standard deviation. If you want to go from variance to standard deviation, you simply take its square root. Now, let's talk about how we could actually compute the variance for a given set of numbers. Now, I do want us to focus on this because I want us to get an idea of conceptually what's going on with this formula. That's important to me. I think it's important for you to know it. As we'll see, the actual calculations for a variance can be pretty freaking tedious. They're nothing at all that an actual researcher or statistician would do in practice. In practice, what you would do is you would Google, how do I do a variance on a calculator, or how do I do a variance in Excel, and you would allow the computer to calculate the variance for you. I am not going to train you to calculate variances by hand. That's not a useful thing for me to do. It's not something you should be paying tuition or money for somebody to teach you. So you do not need to know how to calculate this on an exam. You need to know that relationship I was just talking about between standard deviation and variance, but I will not expect you to calculate either one of those from scratch, from the actual raw numbers. That said, I expect you to understand how the formula works. I expect you to understand why the formula is a sensible formula, and to be able to understand that, I think it's important for us to at least work through one example together. So let's do that. Now, you might remember from the previous formula, right? The variance is that average squared distance from the mean. So we need to first figure out what the mean is. I was a little lazy with my typesetting there. Instead of putting an X with an actual horizontal bar over it, I just wrote out the word X bar. Hopefully you're okay with that. So in this case, the sample mean, X bar, is I just add my 5 numbers up, I divide by 5. It turns out if I do that, I get 80. The sample mean for this example is 80. I need that number to be able to calculate the variance. So here I made a table, and it might look a little crazy at first, but it's a nice, relatively easy way of calculating this variance. So the leftmost column that is titled X, that's just the observations. So we had 5 of them. We had a 60, a 70, an 80, and 90, and 100. So that left column is just my observations. For each observation, I compute X, the actual observation, minus X bar, minus the mean. So for the first observation, 60, I do 60 minus 80. That gives me negative 20. It's saying that the first observation is 20 below the mean. Below because it's a negative number. The second observation is 70. 70 minus 80 is negative 10. The second observation is 10 below the mean. Then I have 80 minus 80, that's 0. The third observation actually is the same as the mean. 90 minus 80 is positive 10. The fourth observation is 10 above the mean. Above because it's positive. And then 100 minus 80 is 20. Now, a sensible question would be this. If our ultimate goal is the standard deviation, if our ultimate goal is the standard deviation, which is the average distance an observation is from the mean. Then it would make sense, wouldn't it, to just take the actual distance every observation is from the mean, add up all those distances, and then divide by n, maybe n minus 1. That's a sensible thing to do. But observe, by looking at that middlemost column, if I total up all those numbers, negative 20 plus negative 10 plus 0 plus 10 plus 20, I get the total on the bottom, which is 0. It turns out that that will always happen. If I try to add up the distances, some observations are below the mean, some observations are above the mean, right? Which means I get some negative and some positive numbers, and those negative and positive numbers tend to cancel one another out. In fact, they'll always perfectly cancel one another out, so we'll always get a 0. So if I wanted to look at the average distance an observation is from the mean, I always get the number 0, which is not informative. The problem is those negative numbers are canceling the positive numbers. So there's a few ways I could address this, but the most commonly used, by far, way of doing it is by squaring these distances. Remember, squaring a negative number makes it non-negative. If it's not 0, it makes it positive. Right? Squaring a non-zero negative number will make it positive. And then now, if I add up the squared distances, I'm adding up a bunch of positive or non-negative numbers. So for example, now I'm moving to the rightmost column. If I take that negative 20 and I square it, I get 400. If I take that negative 10 and I square it, I get 100. 0 squared is 0, 10 squared is 100, 20 squared is 400. So now I have all the squared distances. I add all those up and I get 1,000. That's the sum of the squared distances. Remember that 1,000, it's going to be important in the next slide. So, from the last slide we know what? We know that the sum of the squared distances, that's that sigma symbol of x minus x bar squared, the sum of the squared distance is 1,000. Hence the variance, right, s squared, which remember from a couple slides back, is that sum of squared distances divided by n minus 1 is 1,000 divided by 5 minus 1. That's 250. We're talking about scores on a test, so the units would be points. But the variance, because we squared it, is in squared units, so it's 250 square points. Whatever a square point is, I have no clue. Seems pretty weird to me. And exactly because I'm working with these weird squared units that generally make no sense, I want to take one final step. I want to take that 250, I want to take that variance, and I want to take its square root. Right? We created a problem. Right? We needed to do it to get rid of the negative numbers, but by squaring them, we created a problem. We're now in square units instead of the original units. We fix that problem, we undo that problem by once we're done, square rooting, which of course is kind of reversing the squaring. So I go from the variance, 250 square points, to the standard deviation, which is the square root of 250. That's 15.81. Right? And in this case, right, I go back to my original unit, so it's 15.81 points. Now this is a pretty sensible answer, isn't it? Despite all the calculations. If you think back to a couple slides ago, we had one observation that was exactly the same as the mean. We had two observations that were 10 away from the mean. One was 10 above it, one was 10 below it. We had two other observations that were 20 away from the mean. One was 20 above it, one was 20 below it. So we had two observations that were 10 away from the mean. We had two observations that were 20 away from the mean. So remember, the standard deviation is interpreted as the average distance an observation is from the mean. So if 10 of them if two of them are 10 away and two of them are 20 away, it's pretty sensible to say, well, the average distance that they are from the mean is around 15. Agreed? And so hopefully, again, the calculations are tedious. I wouldn't ask you to do it on a test. But sort of the concept behind it Why do you square those distances? Why do you have to take the square root? The idea that the variance is in these often nonsensical squared units and that the standard deviation is in the original unit. These are things I expect you to understand. The actual definition, conceptual definition of a standard deviation as the average distance an observation is from the mean, that is something that I would expect you to know. And that is a sensible way of measuring variation, isn't it? Right? If there's very, very, very little variation, then that means all the numbers are very tightly packed together. It means they're all clustered together, which means that they're all close to not only one another, but also to the mean. Agreed? Which would mean their average distance from the mean is small. Hence, a small standard deviation indicates a small amount of variation. Now, if there's a lot of variation, if there's a lot of spread outedness, the numbers are spread out very far. They're spread out very diffuse, which means the mean, which would be somewhere in their middle, right, on average is going to be far from these numbers that are quite spread out, and hence would have a large standard deviation. So just to reiterate some facts, the standard deviation is always the same units as the mean and the median, right? So it's in units of inches, in units of dollars, so on and so forth. The variances in these weird squared units, which often don't make sense, right? The variance of someone's height is square inches, whatever that means. The variance of salary would be in square dollars, whatever the heck that is. And so, of course, this means that in terms of actual reports, in terms of communicating with non-statisticians, it's generally easier, it's generally nicer, gives a better interpretation to use the standard deviation rather than the variance. Couple other facts. The standard deviation, as well as the variance, is always greater than or equal to 0. You can see it in the formula basically because we're squaring those distances, and when we take the standard deviation and take its square root, we always pick the positive square root. So when we say average distance from the mean, we're thinking of that as positive distance. Moreover, the standard deviation will only equal 0 when there is literally no variation, when there is 0 variation in the data set, in the variables, which of course means that all observations are exactly the same. The only time the standard deviation equals 0 is if you have the same score throughout your entire data set.